In this video, we're going to start talking about random processes. In order to do that, we're going to go on a tour of frequently encountered and useful probability distributions. So just a review of some probability basics. A probability distribution gives you a summary of all the possible outcomes of a set of all possible outcomes of a set of trials and the probability of each outcome. So usually a probability distribution you'll see summarized in one of two ways, as a probability density function, or if it's a discrete distribution, it's a probability mass function. We'll get into discrete and continuous distributions in a minute. This is just a even more basic than that review. So the probability density function gives you the probability that your random variable is equal to some value for all the possible values of k. And it can be shaped like anything, that's what the normal distribution looks like. It could be skewed over here. And one thing that has to be true about probability density functions, right, is that each point along here gives me, for any value x, under this probability distribution, the probability that a random variable will be equal to that value. And the area underneath the curve of a probability density function has to be 1, because the sum of all of the possible probabilities has to equal 1. It's a fundamental property of probabilities. And the other way we might summarize a probability distribution is using its cumulative density function, which is very similar but slightly different. So for every value, the cumulative density function tells me the probability that my random variable is going to be equal to or less than a given value. Right, so that's the probability that usually starts very small and then eventually ends up at 1. This is what cumulative density functions have a tendency to look like. And they have a maximum value of 1. Right, for large values of k, the probability that your random variable is equal or less than that value is going to be pretty high, intuitively. So there's no rules about what the area underneath this is going to be. So probability density functions are often called PDFs, and cumulative density functions are often called CDFs, especially if you use MATLAB or R, where you might want to know if you're sampling random variables out of a distribution, you use the CDF and PDF functions quite often to do that, but that's probably in an assignment. Anyway, other things we might talk about for probability distributions are the expected value of a probability distribution, which is usually given by E and a square bracket. So the expected value of a probability distribution is going to be the average of all the possible values in the distribution weighted by their probability. So the expected value of a probability density function, I should say, is each of these values, k, weighted by their individual probabilities, which gives you the sort of average expected value of the random variable. So why bother? Right, probability distributions and probability math is weird to think about, so I'm going to try and motivate why we care about this stuff. I'm going to assume you're interested in either building or just understanding models of the natural world or natural processes. And if there's one thing I know, and we all know about the natural world, is that life is full of random stuff. Random processes underlie almost everything that happens to us in our lives, but a lot of random processes do obey a few rules, and well-behaved probability distributions let us model random events like birth and death rates and lottery winnings in a sensible way. And when you're building a model, you need to be able to look at the process you're modeling and say, okay, what assumptions can I make or how much information do I have to let me make assumptions about what kind of distribution is going to best describe the process that I'm modeling. So we're going to talk about some of those distributions that will come in handy, and their properties, and how to know which one to use and when. So I'm going to start with discrete distributions. So a discrete probability distribution is for modeling a discrete random variable, right, where your random variable, capital X, can only take discrete values and not continuous values, usually integer values. So the binomial distribution is for modeling probabilities where every trial has two possible outcomes. Usually we call them success and failure, right? Either the thing you were looking for happened, or the thing you were looking for didn't happen. The ultimate example for the binomial distribution is always coin flipping, right? Because a coin can be heads or tails. Right? Other things you can use a binomial distribution for, something being dead or not dead. So the success and the failure events could be anything as long as they are mutually exclusive and exhaustively. Right? Either one happens or the other happens, but one of the two things has to happen. So the binomial distribution is for modeling if you do a series of experiments where each one has an outcome that's binomial. The binomial distribution is for modeling how many successes you will have if you do a number of experiments. So in words that say we're given a sequence of n experiments. An experiment might be flipping a coin, say, and experiments with binomial outcomes, right? Either yes or no, success or fail, heads or tails. Each experiment yields success. It could be heads or tails, or it could be life or death, with some constant probability p. The number of successes, so the number of times you get heads, or the number of times Schrodinger's cat is dead when you open the box. We're going to call that k. Will be binomially distributed. Binomially distributed. So that's a definition of the binomial distribution, which is discrete. So the probability mass function, because this is discrete, its probability density function if it's continuous. Probability mass function for the binomial is given by the probability that your random variable, so if you actually do an experiment, X is what you actually find, your single realized series of events, the random variable capital X. So the probability that your outcome X is going to be equal to some k number of successes is given by n choose k times p raised to the power of k times 1 minus p raised to the n minus k. This kind of makes sense if you think it out for yourself, considering coin flips. So n choose k, if you think about it, so we've done n experiments, each of which could result in a success or a failure, and we want to know how many of those. We're interested in the ones that resulted in k successes. So n choose k gives you the number of different ways in n experiments you can get k successes. Let's say I flip a coin 5 times, and I want to know the probability that I get 2 heads. Well, there's 5 choose 2 ways for me to get 2 heads in that sequence of 5. P to the k is the probability of 1 success raised to the number of successes, which is the probability of getting k successes. And 1 minus p times the n minus k, that's the probability of getting the rest failures. So it's the probability of getting the k successes times the probability of getting the rest failures multiplied by the number of ways you can do that. Makes good sense. I'm also going to link out to a proof of this for you, but I think it makes good intuitive talking it out sense on its own. What do binomial distributions usually look like? Well, the probability mass function, the probability that your outcome is equal to some number of successes, tends to look a lot like the normal distribution. Now, that was unfair. What I should have done is it tends to be like this, right? Because k, the number of successes is going to be an integer number. So it can, each individual integer number of k will have a value. It's a convention to connect these numbers up, but that makes it look like it's a continuous probability distribution function, which it's not. It's discrete. Anyway. And the range of the function tends to be from 0 up into the number of trials, right? Because if you do n trials, the maximum number of successes you can have is n equal to k. And the cumulative density function, mass function, probably that x is equal to or less than k, looks sigmoidal, like that. And the midpoint of both of these is going to be mu k, the average value of k, the expected value of your result x, which is just going to be the number of trials times the probability of success on each trial, right? If I'm doing this with coin flips, the probability of heads on each trial is 0.5, and if I'm doing 10 trials, then I expect to get half of those heads, so the expected value of my random variable is going to be 5. Right? The probability of success in each trial, 0.5, times the number of trials. And similarly, the variance of the distribution, which will come up maybe less often, is n times p times 1 minus p. The second discrete distribution I want to talk about is the geometric distribution. This one's a little bit more fiddly to define. So if we, given that the probability of success on any given trial, probability of success is always p, the geometric distribution gives the probability that the first success happens on the kth trial. So let's say on any given day there's a constant probability that you're going to be eaten by a lion. Then the probability that it takes 20 days before you get eaten by a lion will be geometrically distributed. You can also think of it in another way. It's also the probability that you fail k minus 1 times before you succeed. So the geometric distribution is kind of an extension of the binomial distribution, where you care about how many failures in a row you get before the first success. Like a waiting time kind of problem. So the probability mass function is given by probability that x equals k is given by 1 minus p to k minus 1 times p. Again, you can think this one out pretty straightforwardly, because what happens if you succeed on the kth trial means that you fail 1 minus k times, or you fail k minus 1 times, rather. So if p is the probability of success, 1 minus p is the probability of failure. So you need to fail k minus 1 times, p to the k minus 1, and then succeed. And there's no binomial coefficient at the front because there's only one way to do that. So those distributions, px is equal to k, they tend to look like this, right? Where for any given value of p, for any probability of success, you're more likely to have your first success early than you are to have your first success late. And the steepness of this curve is going to depend on the probability of success. So if your probability of success is high, like say it's 0.8, then most likely you're going to have your first success early on. Sorry, this is k, the number of trials. Whereas if probability of success is smaller, then it's more likely that your first success will come a little bit later on. And the cumulative density function, x is equal to or less than k, they tend to look like this, a saturating curve, where the higher the probability of success, the faster you get to 1. I'm running out of space, so we'll go over here. So I'm still talking about the geometric distribution. It's alright. If we know the probability of success in each trial, what's the expected number of k, the mean number of trials before you expect to see success? So what's the expected value of your random variable x? It's just going to be sometimes, right, called mu x, the mean of the probability function. It's just going to be 1 over p. This also makes sense to me intuitively. I'm not going to prove it to you exactly. But again, if you think about coin flips, where p is equal to a half, the average number of trials it'll take you before you get a heads is 2. 1 over 1/2, which is p. In fact, I think I'll have you prove this to yourself using simulation in the homework assignment. Aha! And the variance of a geometric distribution, so the variance in your random variable x, given by sigma squared x, is going to be 1 minus p, the probability of failure, divided by p squared. Right? As I remember, the geometric distribution is useful for things like waiting times. If you know that the probability of an event is p, the geometric distribution models how long it takes before you get the first success. So if your annual probability of being eaten by a lion or having a baby is constant, then the time until you die or the time until you have your first kid is going to be geometrically distributed. The last discrete distribution I want to talk about is the Poisson distribution, or the fish distribution if you're from Canada. It is a little bit more nuanced. It's actually an approximation to the binomial distribution for when n is large, lots of experiments, and p is small, the event that you're trying to find is rare. The definition is a bit long, so bear with me. So if the probability of success p is an average rate over time or space, average or rate, and it's independent of when the last success happened, right? Independent of the last success. The probability of a given number of successes, k, in a given interval of time, in a fixed interval of time, will have the Poisson distribution. So it's the probability of k successes in a given interval. Is Poisson distributed. So the biggest difference between this and the binomial distribution, in the binomial we said you've done n trials and you want to know what the probability of there being k successes is. In the Poisson distribution, you're assuming effectively an infinite number of trials, and you want to know the probability of getting k successes over some interval of time. For example, given how rarely I get phone calls, the number of phone calls I receive in a day is probably Poisson distributed. The number of prairie dogs in a square mile of habitat, probably Poisson distributed. Although maybe not, because they do tend to club together. Maybe, well, what's solitary? The distribution of mooses in a square kilometer of territory might be Poisson distributed. So it's for events that are rare. So this is an approximation of the binomial distribution when n is large and p is small, for modeling rare events. Right, and the mean and the variance of this distribution are both n times p. The mean number of successes is always going to be, in this case, n is the length of the interval of time, not the number of trials, say, exactly. It gets a bit wibbly. But the length of the interval times the probability of that happening in any given interval is the expected value of your Poisson distribution, which also gives you the variance. Right, the mean and the variance of a Poisson distribution are always equal to each other. So the probability mass function, probability that x is equal to k, probability of k successes in a given interval of time, is given by e to the negative p times p to the k divided by k factorial. I'm not going to prove it to you. I'm probably going to link out to a proof or get you to prove it in a homework assignment, but this is the probability mass function for the Poisson distribution. So what's it going to look like? Px equals k is going to tend to look sort of binomial distributed around n times p, where p is the probability of success and n is the number of trials or the size of the interval you're looking over. So depending on the probability, this could be shifted and maybe skewed this way. Yeah. But it tends to look like a discrete, symmetrical, normal distribution kind of thing. And the cumulative distribution, px is less than or equal to k, is another saturating type of curve depending on what the value of p is. If p is quite high, then it saturates quickly. If p is low, you get something more like this. And again, this should have been a dotted line. I'm used to smoothing out dotted lines for but it's a discrete distribution. Important to keep in mind. Now we come to the continuous distributions. So where discrete distributions describe random variables that have only a discrete set of possible outcomes, usually success or failure, right? 0 and 1 binary variables. Continuous distributions are for describing random variables whose outcomes could be anywhere along the real line. Right? Not whole things, but like continuous random variables might be the height of a person picked at random in a room, or the mass of a randomly selected rock, or the mass of a baby turtle. So where before I was talking about probability mass functions, now I can talk about probability density functions. So the first continuous distribution can actually be either discrete or continuous, and it's the uniform distribution, which just means if a random variable is uniformly distributed between values of a and b, if x is uniformly distributed between two values a and b, most often it'll be a uniform distribution between 0 and 1, which we say x is uniformly distributed between 0 and 1. That's what that looks like. That means that all values in this range are equally probable. So for anything in this range, the probability of x equaling that thing is a constant. So I'm going to do this visually. Right, the probability that x is equal to k. So here's 0, here's a, here's b. This is some big number. For any k in between a and b, the probability is constant. It also means the cumulative distribution function, right? Probability that x is equal to or less than k. Here's 0, here's a, here's b, here's some big number. You're just going to get a straight line between a and b. So given that we've defined the uniform distribution to make this true, that means that the probability density function is given by, at any point between a and b, 1 over b minus a. The expected value of the uniform distribution is going to be what? Well, it's going to be right in the middle of this, right? So that's going to be a plus b over 2. And the variance of uniform distribution is b minus a squared over 12. So it's just an odd fact that this uniform distribution up here, the one that we use most often in simulating things, the variance of that distribution is 1 over 12. Fun fact. So the uniform distribution doesn't come up so often as a thing that describes a particular natural process. It's more like the null distribution. If nothing interesting is happening and you don't know anything about your probability, the process that's underlying your probability, you might assume a uniform distribution as a kind of null model. And now we come to the normal distribution, or Gaussian distribution, everyone's old friend. So the normal distribution is kind of the odd man out in this little spiel of mine, because instead of it being defined based on some probability of success in a given trial, or something like that, the normal distribution describes the distribution of a random variable that is clustered around some value mu with some known variance sigma squared. So the distribution of a random variable with values clumped around its mean mu with a variance sigma squared. Alright, it's the classic bell-shaped symmetrical continuous distribution. So the probability density function, probability that the random variable is equal to some value called k, is actually given by this huge big ugly thing, 1 over the square root of 2 pi sigma squared times e all to the negative k minus mu squared over 2 sigma squared. I'm not going to prove it to you because it looks awful, but I will link you to a proof, I promise. But just to go through it for a second, right, pi is pi, sigma squared is the variance of the distribution, k is the value whose probability you're interested in, and mu is the mean of the distribution. So I think I missed out all these subscripted x's here. Right. That's fine. And the standard normal distribution is where mu is equal to 0, and sigma squared is equal to 1. And you probably all know that this probability distribution function tends to look like this. Nice, beautiful bell shape, centered around mu. And these actually go off to infinity, even though by the tails probabilities are very, 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 very small. And the variance, so mu controls where the top of the hump is, and the variance controls how wide this is. So if the variance is smaller, you get a higher peak and less of a spread. And the cumulative density function, x is equal to or less than k, tends to be sigmoidal, where if you have quite a bit of variance around your mean, cumulative distribution function is sigmoidal, and if there's less variance, then it tends to be more of a step function. Say that sigma squared equals 0.1 and this one's sigma squared 0.5, something like that. The higher the variance, or the smaller the variance, the more compressed both of these functions become. And we use the normal distribution for all kinds of things that have a strong tendency towards their mean value and some known amount of noise on either side, random noise. For example, the values of continuous traits, continuous genetic traits, we tend to assume they're going to be normally distributed. Like, classically, if you get a group of human beings of the same sex in a room, their height will tend to be normally distributed. Human mass tends to be a little bit normally distributed, that kind of thing. So, where the Gaussian, or the normal distribution, is a continuous time analog to the binomial and Poisson distributions, the exponential distribution is a continuous time analog for the geometric distribution. So if you remember, the geometric distribution was for the distribution of the waiting time until the first success. So if you're flipping coins, how many flips does it take before you get a heads? Or if there's some chance you're going to be eaten by a lion, how many days are you going to last? So in the continuous time sense, if successes occur randomly at some rate, so instead of there being a discrete probability of success, successes are happening at a rate over time, some average rate over time. So if successes occur randomly, over time at a rate, we're going to call that rate lambda for now, time until the first success has an exponential distribution. A common exponentially distributed trait might be mortality risk. So if my probability of dying is a given, if I'm dying at a set rate lambda, then the time until the first success, I only get to die once, hopefully, the time until the first success will be exponentially distributed. So it's just like the geometric distribution, but continuous. So, and the distribution is given by the probability density function. Probability that x is equal to k is going to be lambda, the rate of successes, times e to the negative lambda times k. So if I'm talking about death rate, right, this is the probability that I die at time k is going to be the mortality rate times e raised to the negative mortality rate times k. Right, and the two important properties of our distribution, its expected value and its variance. The expected value of the random variable x that's exponentially distributed, is going to be 1 over lambda. And the variance of the random variables distribution is going to be 1 over lambda squared. What are the probability density functions going to look like? So the simple probability density function, x is equal to k, tends to start high and just go down over time. right? Because we're waiting for our first success, so it's less likely that the first success is going to be far out in time, and more likely that it'll be early. And the steepness of this curve, so let's say this one is for an event that happens at a rate of 1 per time step, something that happens less often, less frequently, say lambda's smaller, it's going to have a less steep drop-off, because it's still quite possible if at each time it's unlikely to happen, the first one could happen quite far out in time. Similarly, if lambda is quite big, lambda is equal to 5 there, then it starts to turn into an L-shaped curve, because if the probability of it happening over any time period is quite high, then it's going to happen early on, most of the time. And the cumulative density function, probability that x is less than or equal to k, is predictably going to be a saturating function, the steepness of which is dependent on lambda. So if lambda is small, it's not going to be very steep, and if lambda is big, it'll be quite steep. The last stop on our whirlwind tour of probability distributions is the gamma distribution. So the gamma distribution is closely related to the exponential that I just talked about, but instead of wanting to know the time until the first success, I want to know the time I have to wait until the nth success. So let's say I'm watching a herd of gazelles, and there's a constant probability that one of them is going to be eaten by a lion. I want to know how long I have to wait until 3 of them get eaten by lions. Not just, I don't care about the first one to get eaten, I want to see 3 get eaten. So in that case, you want a gamma distribution, which is a 1-step more complicated exponential distribution. So, phrased more mathematically, if successes occur randomly over time at a rate lambda, so if successes occur at rate lambda, the time until the kth success not the first one, the kth one, follows a gamma distribution. So this probability density function is a lot less intuitive to look at. So let's say for the probability density function, let's say the probability that x is equal to t, right, because we're looking at the time until the kth success, is equal to e to the negative lambda times t times lambda t times k minus 1 divided by k minus 1 factorial all times lambda. That's an ugly mess, and I'm not going to prove it to you. But that is the way the probability density function for the gamma distribution looks. So important properties of the gamma distribution. The expected value of the gamma distribution is given by k over lambda, the rate of successes, the number of successes you care about divided by the rate at which they happen, and the variance of the distribution, the variance of it, the random variable x, is the number of successes you care about divided by the rate squared. And what does it look like? Gamma distributions can take lots of shapes depending on the values of your lambda and your k. Right, it's possible to get one that starts off really high and goes down, and that's if the probability lambda is quite high and k is maybe low. So if you only care about the second one and the probability is high, it's going to happen early on most of the time. Right? Or you can end up with more bell-shaped looking distributions if, say, the rate is quite small. This starts to look kind of Poisson distributed because the Poisson distribution is for rare events. Anyway, depending on the 2 parameters of the distribution, the shape will change quite a bit. And the cumulative density function, probability that x is equal to or less than t, tends to be straight saturating, depending again on what the values of lambda and k are. As always, if lambda is high and k is not so high, it'll saturate pretty quickly. If lambda is small or k is large, it'll saturate in a more sigmoid way. Mostly what I want you to keep in mind about the gamma distribution is it's a generalization for if we care about successes beyond that first one. For example, say in PCR, right, DNA strands are synthesized at a rate of like 1 per millisecond, so the time until you've got 1,000 new DNA strands is going to be gamma distributed. Or if you've got that herd of gazelles I was talking about and they get eaten by lions at a known average rate, then the time it's going to take for all the gazelles to be gone is going to be gamma distributed. That sort of thing. So that's all I really wanted to say about the simple distributions I've talked about. So always ask yourself, first, is the random variable I'm trying to model discrete or continuous? And then, am I worried about the probability of the event happening at all? Am I worried about how long it's going to take for it to happen? And then finally, am I worried about how long it's going to take for it to happen multiple times? And now you have distributions for all possible combinations of those things. And I think that's all I have to say about that.